Okay, so everybody listen. Everybody listen. I'm going to give you some more gifts. More gifts. But I'm not sure I have enough for everybody, so the people who are in the front get precedence. And of course, Monica gets precedence. So I'm going to pass this stack of papers about. Now, one of them is a more extensive table of the fundamental constants. And the other one is a periodic chart, the best periodic chart in the world. Made by NIST, of course. So pick one and pass it on.
Okay, so
And Monica gets a card.
we would like to start thanking you for coming to Brazil and give us this seminar. I want to explain to you that we made the seminar in the room because it's supposed to be a more specific seminar. It's not a colloquium or anything, so that's why we want to have the audience that are really interested in this kind of physics. But there will be a few lectures that are more broader, and you can come to, so we hope. I don't think Bill needs a lot of introduction, but he's
That's not going to stop you, is that what you're saying?
Well, he is also from MIT, from graduate school, and then he moved to NIST, and he's been a very good physicist with a very nice recognition internationally. And Bill is one of the beginners of laser cooling.
And I'm still a beginner.
Yeah, but you begin later. And he idealized techniques for us to cool atoms, and today, this is one of the largest field of physics, at least counting by publications. It's a very hot topic, including cold matter. And he's coming to Brazil a few times, and as you all know, he got Nobel Prize of Physics because of this work. And we are all very happy that he can come and have this enthusiasm, as always, to discuss physics. And today his seminar will be about one of the experiments they are doing at least. I don't know if you're going to just tell us a little bit about the whole arrangement, at least, and University of Maryland. But they do a lot of work in cold atoms, as you know. And today he's going to tell us about these spinning atoms when you have angular momentum in the light and produce some nice quantum effects. And so we are all... I'd like to know if you prefer questions at the end, or if you could somehow...
No, I think that for a small group like this, if anybody wants to ask a question, just shout or whatever, and I'll try to answer.
Okay, so let's go.
Okay, so I'm going to tell you about spinning atoms with light. Of course, this is in honor of the 75th anniversary that we're celebrating this week with a series of seminars. This work that I'm going to be telling you about was done in collaboration with Chris Homerson, whom I think a lot of you know because he was just visiting here recently, and Michael Anderson, who's now in New Zealand, Pierre Cladet, who's in Paris, Vasant Natarajan, who's in India. Anand Ramanathan is a graduate student, and he's the only one who's still around, so he has to do all the work. And although we now have Sergio pleased to collaborate on the extensions of this project. And some of you know Sergio as well, and Chang Ru, who's at Los Alamos Laboratory, and Ali Pasha Vaziri, who is now at the Howard Hughes Medical Institute in Janeiro Farms, Virginia. So this is the senior people of the laser cooling group. Here's Chris Homerson, Paul Lett, Ian Spielman, and Trey Porto are the senior members of the group. And we're part of a new institute called the Joint Quantum Institute, which is a joint between the University of Maryland and NIST. And those of you who are familiar with JILA, it's sort of like that, except with NIST in Gaithersburg and the University of Maryland. And we have a wide variety of activities in both atomic physics and condensed matter physics and some other areas, all focusing on the idea of quantum coherence. So what I'm going to tell you about today is what I like to call rotational Bragg scattering. It's a new tool for manipulating coherent matter, which is to say a Bose-Einstein condensate, but one could presumably use other atomic samples using coherent light, which of course is a laser. And just to provide a little bit of introduction, although I suspect for this audience I don't need very much introduction, I want to recall a little bit of the history of manipulating atoms with light, which goes back a very long way. And in fact, just last night we were talking about Zeeman's original work, and here is a 1987 paper in Nature. You should really look this up. These old papers are magnificent. So he begins the paper saying, in consequence of my measurements of Kerr's magneto-optical phenomena, the thought occurred to me whether the period of light, and by period he means wavelength, whether the period of light emitted by a flame might be altered when the flame was acted upon by magnetic force. And by magnetic force he means what we would call magnetic field. And so he says he puts it in a magnet, and when he closes the circuit on the electromagnet, both D lines were seen to widen. And then later in the paper he says, I've since found by means of a quarter wave plate and an analyzer that the edges of the magnetically widened lines are circularly polarized when the line of sight is along the direction of the magnetic field. So all of that, you know, just with a flame and an electromagnet. Now we understand the quantum mechanics of this. You have an excited P state that is split in the magnetic field, and the broadening comes from this splitting, and the circular polarization on the edges of the broadened line come because of the selection rules on angular momentum when the light is fluorescing from these upper states. So this was the first exchange of angular momentum between the light, the circular polarization of the light, and the electron motion in the atom, the spin of the electron. Now this is rather interesting because this is 1897. Most people were not convinced of the atomic theory at that time, and this was a very important experiment for establishing the idea that atoms were made up of electrical charges that might move around. And so Zeeman's experiment gave confirmation to that hypothesis that there were atoms and the constituents of the atoms were electrically charged. Here's a picture of Zeeman with some people that you might recognize in his laboratory. Well, a little bit after Zeeman, a few decades after Zeeman, another way of manipulating atoms with light, or at least transferring momentum from light to atoms, came from Otto Frisch, who had an atomic beam, and he had a lamp, a sodium lamp, that he would shine on the atomic beam, and he looked at the deflection of the atomic beam due to the momentum transfer from the light to the atom. Now we think of this as being our bread and butter. This is what we do every day in the laboratory, is change the momentum of atoms with light. This was the first time it was done in 1933, and this was the beginning of manipulating the linear momentum of atoms using light. But of course it was done with a lamp. But interestingly, this experiment, here you see the two beam profiles before and after the illumination with the lamp. You see it was shifted over a little bit, and here's the difference. So you can see it's very clear that it was shifted by absorbing about 1 photon. And this experiment didn't improve until people had lasers. So this was the best experiment for manipulating atoms with light until there were lasers. Well, all of these early experiments, Zeeman's experiment, Frisch's experiment, were done with incoherent light sources, flames and lamps and such, and incoherent atoms, thermal gases, and thermal distributions of internal states, as well as center of mass motion. Establishing coherence was one of the things that came with optical pumping. Now, here's a very simple example of optical pumping. If you have an atom where the ground state is double at S1/2 and the excited state is double at P1/2, then with circularly polarized light you can pump the atoms into the m=1 state and make a pure internal state. So optical pumping allowed people to make pure internal states. Of course, Kastler, the laboratory that Christoph is from, is named after Kastler and his colleague Roussel. Once they were able to pump atoms into a pure state, they were able to coherently manipulate the internal state of the atoms using, for example, radio frequency or microwave. And that was one of the things that made the reputation of that laboratory, was doing these kinds of experiments back in the 1950s. But the real revolution in coherence came with the advent of the laser. And now you had light that was not only spatially and temporally coherent, but having that kind of light made possible things like laser cooling and the production of atomic samples that had coherence of their center of mass motion. And of course that came with Bose-Einstein condensates. And here is the famous 3 pictures of a thermal gas, a gas that's partially condensed, so it has both thermal and a coherent component, and when you cool it enough, you have a nearly pure condensate. And of course, these guys got the Nobel Prize for doing that. So all of this is very quick because I think everybody knows all of this. We could compare a Bose condensate to a laser, but I don't think I need to do that. Let me just tell you the general procedure that we use when we do experiments with Bose-Einstein condensates. First, we form our condensates by evaporative cooling, typically in a magnetic trap, but in more recent experiments in optical traps. Then typically we release the Bose condensate from the trap, although that's not always necessary. It depends on the experiment that we're doing. And then we use some manipulation, which I will say more about, that will manipulate the momentum of the atoms. And then we, after a time of flight, after having done this manipulation, we take a picture of where the atoms are using usual absorption imaging, shadow imaging. And if the time of flight is long enough, that spatial distribution gives us the momentum distribution for long enough time of flight. One of the things that we have developed in our laboratory for manipulating atoms in this way is Bragg scattering. In Bragg scattering, we have the atoms of the condensate here. We illuminate the condensate with counterpropagating beams, one of which has frequency omega, and one of which has a frequency omega plus delta. The atoms absorb a photon of frequency omega plus delta. They are stimulated to emit a photon of frequency omega. In the process of absorption and stimulated emission, the atoms gain 2 units of photon momentum. So the atoms are moving in this direction to the right. And the difference in energy of the photon here, omega plus delta, and the photon omega, provides the kinetic energy that the atoms pick up as a result of getting the momentum kick from these 2 photons. So one way of thinking about this process is as a kind of Raman process, where the atoms starting in the ground state, the ground electronic state, and here I'm showing the momentum of the atom, and here's the energy of the atom, which is the kinetic energy plus the excitation energy. So here's an excited state. Of course, this is not to scale because this is several times 10 to the 14 hertz, and this energy along this direction is 100 kilohertz. But the atom absorbs off resonance and is stimulated to emit back down to the ground state in this state that has non-zero momentum and a certain amount of energy. And for sodium, the energy that's needed is 100 kilohertz. For rubidium, it's, 16 kilohertz. So it depends on your atom, but it's a very tiny amount of energy compared to the energy of the photon. And here's an example of experimental results. Here we have a Bose-Einstein condensate. Then after applying this pulse, which lasts a few 10 microseconds, and waiting for a time of flight, then the picture looks like this. Here's where the condensate used to be. Here's the atoms that have absorbed and emitted photons. So this shows how much momentum transfer there was, which you can measure, and you find that it's within experimental uncertainty, it's exactly 2 photon momenta. And just to assure you, we deliberately left behind a few atoms. We can make all the atoms do this process, or any fraction that we want. We deliberately left some behind just so we could see where zero momentum was to make the calibration easier. And this kind of Bragg scattering has been done for many years on non-coherent samples, that is non-Bose condensates, thermal atomic beams. Dave Pritchard at MIT, Sue Ali at Colorado State University did some of the early experiments on that.
Bill,
Yes.
just for clarifying, most part of the people are using the notation Bragg scattering in a different context.
Okay, so maybe I should say something about that.
Why we use Bragg
Why we use
scattering
that, right.
for this?
Right, so, okay, so let me say, I'm glad you asked that question. So normally we think of Bragg scattering as taking X-rays and shining X-rays onto a crystal, and then the X-rays have to reflect from the planes in the crystal. And then the interesting condition is that the reflection is specular from the planes of the crystal, but it only works when you adjust the angle of input of the X-rays so that the specular reflection from each plane adds coherently. That is, where you have constructive interference. Now, why is that like Bragg scattering that I'm describing here? When I have two laser beams that are counterpropagating, of course they interfere with each other. Now, these two laser beams don't make a standing wave because they have different frequencies. But let me go into the reference frame that is moving with the interference pattern. That's a reference frame where you move in this direction to the, you move in this direction to the right, in such a way as to Doppler shift this beam down by delta over 2 and this beam up by delta over 2. So the two lasers look like they have the same frequency. Then in that reference frame, moving along like this, it looks like you have a standing wave. Now, that standing wave looks like a bunch of parallel planes, like you have in a crystal. And the atoms are moving compared to that plane. And the atoms come in and Bragg reflect off of those planes and reverse their velocity. And that reversing of the velocity in the moving frame is the same as changing the velocity from 0 to 2 photon recoil momenta in the laboratory frame. And the correspondence with Bragg scattering is very close. The choice of angle when you scatter X-rays off of the crystal is equivalent to choosing the frequency difference between the beams so as to conserve energy. The conservation of momentum is guaranteed by the specular reflection, but the conservation of energy is guaranteed by the change in the angles. So in the experiments that were done with atomic beams, this was more clear, because they had an atomic beam going along, and then they had laser beams making a standing wave at an angle. And the angle that they tilted it to was the Bragg angle. Now, if some of you use acousto-optic modulators in the laboratory, you know you have to tilt the acousto-optic modulator until you get the right Bragg angle to get Bragg reflection of the laser beam from the sound wave that is in the acousto-optic modulator. You have to tilt the angle. Well, they had to do the same thing. They had to tilt their laser beams to get the right angle. If you now go into the reference frame of the atom moving along with the atomic beam, then it looks like the Bose condensate. And when it enters the beam, it sees two different frequencies because of the Doppler shift. So that's the connection between Bragg scattering of X-rays on crystals and Bragg scattering the way we describe it. So it's really exactly the same thing, but it doesn't seem that way when you first look at it. So I thank you very much for asking that question. Okay. So now what we're going to do here in this experiment that I'm describing today is add another feature to this Bragg scattering process. And what we're adding is angular momentum, but not angular momentum due to the polarization of the light. Instead, angular momentum due to the mode structure, the spatial mode structure of the light. And in that way, we're going to add angular momentum to the atoms, not in their internal motion, but to the whole spinning of the whole cloud of atoms that constitutes the Bose-Einstein condensate. So here is a picture of and a description of what orbital angular momentum of light is. Now, how many people here have heard about orbital angular momentum of light? About a little less than half. Okay. Okay. So so maybe I'll go through this a little bit slowly. So ordinary light, the light that comes out of a laser like this one, is a Gaussian intensity profile, and the phase fronts, that is, if I looked for planes of constant phase, they're almost flat for a laser, a collimated laser like this laser pointer. And that's what's indicated here in this picture. Is I have a few planes that are planes of constant phase, and this is supposed to be a movie, and with great effort from Fred yesterday, we almost got it to work. I think that if I go into my regular thing, I might be able to make this this movie work. Here, let's go here. Okay, so I'm going to try to play this movie, so you can see what. Okay, so that is, yeah. So that shows you what the what happens now. Over here on this side, I hope this isn't too small, because I want to play the movie before I go back to the full-size version. Over here we have a kind of a donut mode. But this donut mode has a very special character to it. If I were to take a plane perpendicular to the direction of propagation of the beam and ask what is the phase of the light as I go around, that phase winds up by 2 pi in going around once. And here's the expression for the field that shows that there's a 2 pi phase winding as I go around in the azimuthal direction. It also shows that at the center there's no intensity, and then the intensity grows and then falls off like an exponential. This is called a Laguerre Gaussian because there's a Gaussian profile and then there are various Laguerre functions that multiply that. So if I ask now what are the planes of constant phase, or the surfaces I should say of constant phase, they look like this corkscrew here. And when the light propagates, it propagates like this. Okay? So this one propagates like this, and this one propagates like this. Now let's see if I can come back to the slideshow. Oh, great. Oh, wonderful. We're sorry for the inconvenience, it says. PowerPoint has messed up and has to close, and we're sorry for the inconvenience. Okay, so now I'm going to have to, I guess I've just rebooted PowerPoint. Great. Okay, close. Would you please close? Damn. Okay. Okay, so while that's loading, let me tell you a little bit. Let's see, where's the light switch here? I need to have you see me. So if you've got this sort of corkscrew setup of constant phase, then what it means is that the pointing vector is not pointing in the same direction on the 2 sides of the beam. So if I've got flat phase, then the pointing vector is like this, but if I've got a curved phase, the pointing vector is like that. And you can see now that if this thing impinges on some surface, it's going to impart a torque to that surface. So that's one of the ways of understanding how it is that such a beam has angular momentum. And that's what we're going to use. Okay, so now we're back in business, I hope.
Excuse me.
Yes.
How do you generate these?
That's the next slide.
Okay.
So it turns out that there are a lot of ways of generating these things, and in the 1990s, people started to figure out how to do this. Now this was really interesting, because of course, we've understood electromagnetism since the time of Maxwell, and the ways in which electromagnetic fields propagate. And the angular momentum of an electromagnetic field, the general expression, was understood and was written down in all sorts of textbooks. But people really didn't start to make these kind of beams that have orbital angular momentum until the 1990s. And there were all sorts of ways of doing it using cylindrical lenses and phase masks and stuff like this. And one of the best ways that was developed, and one of the most convenient ways, is to use a hologram. So the hologram looks like this. Now, the nature of this hologram is, it just looks like an ordinary diffraction grating, except there is a defect in the diffraction grating where you go from having a certain number of diffraction lines to having one more on the other side. Now, what the nature of this thing is that it diffracts something in the direction you'd expect a diffraction grating with this period to have, but in addition, it gives it this angular momentum. Yes?
Seems like a dislocation in crystal.
That's right. It's just like well, I wouldn't say it's just like a dislocation in a crystal, but it's very much like a dislocation in a crystal. Exactly. It certainly is a dislocation or a singular point or something like that. And a little bit later, when I show you how we interfere rotating and non-rotating clouds, I'll make it a little bit more clear why this pattern will diffract a rotating light field. But this is how we make it. We shine the light onto this diffraction grating, and what comes out is a Laguerre Gaussian. Here's a picture of various diffracted orders from a diffraction grating like this. The undiffracted one, of course, is the Gaussian. The first diffracted order has one unit of angular momentum around the axis. The next one has 2 and 3. And you can see that they are wider, which means they're a higher order Laguerre Gaussian. Every photon, if you want to think in photons, for the lowest order Gaussian mode, the one that I described here, every photon has 1 unit of angular momentum along the axis of propagation. Eduardo?
What's the efficiency to do this, the Laguerre Gaussian? Like the efficiency of your input to your output?
Oh, the efficiency. Well, yeah, that's a good question. I'm not sure I know what the best you can do, but I believe that with a well-constructed grating, that you can get efficiencies in the order that you want, that's on the order of 70%. But is there anybody here that has used these things besides who might be able to answer that one better than I? But it's reasonably high efficiency. Here, for this picture that you see here, it obviously wasn't such a high efficiency. Most of it was going straight through. But you know, if you blaze a grating, there's a lot of ways that you can do it so as to make the efficiency higher. And I think that if you work really hard, at high efficiency, you can get something that's pretty good. But I'm not sure, so don't take that as...
So what did you change between Laguerre Gauss 1, 2, and 3?
Well, here it's just different orders. It's just different diffraction orders.
Okay, so you just tilted the grating?
Well, in this case, the grating, no, the grating just makes all orders by itself.
By itself.
It's just an ordinary diffraction grating, a thin diffraction grating, so it just makes all the orders by itself.
Okay.
So the first order is a 2 pi around the...
Right, the second order is 4 pi around, yeah, exactly. Okay, so,
yeah. A kind of stupid question, but if I have a Laguerre mode beam propagating, the flux of momentum is not exactly axial. That's what we were saying, right? Because to transfer angular momentum, somehow you have to be able to have the gradient of the phase, which means momentum being transferred perpendicular to the propagation.
Yeah.
So how is the vector, you know, like equivalent to the point vector for a Laguerre mode?
Okay, well, in fact, I think I might even have some pictures of that someplace as to what what it looks like. But it's sort of the way I was trying to do with my fingers as to what so what happens is, in the center, of course, there's 0. Okay, now as I move out from the center, I get a little bit of pointing vector, and it's tilted a little bit. And as I continue to move out, it grows. I'm not doing a very good job of making it grow, and then it shrinks again, but it always remains tilted. Now I can't tell you for sure whether the tilt changes as I go out. I just don't remember. one could figure it out if necessary. But I think that behind your question is a deeper question that says, how should I think about the propagation of linear momentum and angular momentum in such a beam? And the answer to that question, from me, is I don't know. I've been puzzling over this for quite some time because I don't really understand how I should think about the angular momentum in this beam. For example, let's say that
I just take E cross E. That
Yeah.
will not be the linear momentum here. Right?
Well, that's the pointing vector, which is not exactly the same as.
No, but is the direction of K.
It's the direction of, well, remember, K is not a single value here. K is only a single value for a plane wave. So I've definitely got a mixture of different Ks in here.
Changing as you
And not only changes its, it changes its tilt as I go around it. Even in the Gaussian beam, K is different across the beam. If I'm in the far field, if I'm in the near field, I've got a mixture of Ks, even if the phase front is flat. So correlating K and momentum is a little bit funny in a light beam, especially if you're in the near field. If you're in the far field, you can use ray optics, and you can say that every ray has a certain K value. But if you want to look at the whole thing, it's a little bit.
in fact, you have a gradient of phi of the phase.
Yes.
That will add something.
Yeah, and that, of course, is the key thing that distinguishes these beams from other ones. But the fact is, I have not come up with a way of thinking about it myself that I find completely satisfying.
There is a nice PRL paper of 2008 which comes back to this problem in the general trend, explaining this sort of thing.
And whose paper is that?
Someone I don't know.
Oh, okay.
From the US,
There's a whole book.
Theory paper, but it's quite nice.
Yeah.
Actually,
Okay.
We can find it.
Okay, there's a whole
There are some
book.
theories that we cannot
Yeah.
really follow.
No, but this one
This
has
one is
some physical content.
Well, there's a book called I think it's called The Orbital Angular Momentum of Light, that is a collected set of works that was collected by some of the Scottish people who did a lot of the early work on this. So that's another resource for trying to understand this. But angular momentum in light, it's a funny thing because sometimes it's not so easy to distinguish between orbital and spin. By spin I mean polarization. But sometimes it's not so obvious because it also depends on what axis you choose. Spin doesn't, but this does, and funny things. And I've talked to Emil Wolf about this and come away unsatisfied. But
Probably it is because we are biased by plane wave.
Maybe so. That's right.
Here we have a finite system, and finite system has a momentum spread distribution,
Right.
and you can tailor this
Yeah, maybe that's,
Fourier plane.
our mind always focuses.
that's right. A plane wave is definitely not the way to think about this. It's a
Cannot work
very
with plane wave.
yeah.
Dislocation on the plane wave.
Yeah, that's right.
I have another question about the generation of this beam. I mean, momentum, angular momentum has to be conserved.
Right.
So
So where does it come from?
Yeah, I mean, the grating.
Yeah. Well, okay. Let's go to just let me turn the light off. So here in this grating, I think there's no problem because you generate as much negative stuff as you do positive stuff. But then you're going to ask, well, what if I blaze it in such a way that I get most of the stuff in the direction? Well, what's going to happen is you're going to have to generate a torque on the diffraction gradient. I mean, it's the only place it's going to come from. And in fact, people have done experiments where they look at the macroscopic mechanical effects of the orbital angular momentum of light on stuff. And here's an example of that. So what we're looking at here, you can barely see it, but when I run the movie, I think you'll be able to see it. There's a clump of microspheres that is being held in an optical tweezer, but you've got orbital angular momentum of light in that light field, and now you can see it rotating. See, so the orbital angular momentum of light is causing that clump of particles to rotate, and they switched the sign of it there.
Yeah, but that's when you have angular momentum already in the light.
Yeah, Right, so the
Yeah,
light...
you just try to make an analogy.
And right, so I'm just trying to make an analogy that we can actually see the mechanical effects. If you, for example, take a quarter wave plate and shine linearly polarized light into it, you can measure the torque on the quarter wave plate as it transforms the linearly polarized light into circularly polarized light. So in terms of conservation of momentum, it's the same sort of thing. It gets transferred to the device that's making it. And you know, that's something that people have done. You suspend a quarter wave plate in a vacuum on some kind of magnetic bearing, and you shine light through it, and the quarter wave plate will start to turn. So the same thing would happen here. I don't know if anybody ever did it with a diffraction grating, but here's an example of where the mechanical macroscopic effect is seen on a macroscopic object. Well, so there's been here's a few of the references for macroscopic objects, but people have also done it on atoms. And this is just one example of a case where the orbital angular momentum of light was seen to be transferred to atoms. And I'm not going to go into the details of this experiment, which was done by Mikio Kozuma, who's an alumnus of NIST, and now in Tokyo. And what they showed was that after they prepared the atomic sample in a certain way, when they send in a Gaussian beam, that it will come out as a Laguerre Gaussian beam. And indirectly, by seeing the effect on the light, they can tell that there must have been some momentum transfer to the atoms. But this was a thermal gas of atoms. And so the effect on the atoms was never seen directly. And that was true for all of the experiments that, up until recently, were involving the transfer of orbital angular momentum of light to mechanical rotation of a cloud of atoms. It was never seen directly on the cloud, but only indirectly through the effect of the light. And that's now what we're going to do, is to show the effect directly on the atoms. And one of the advantages we have is that we're using atoms that are Bose condensed. Whereas if you can imagine that if they're in a thermal cloud, seeing a little bit of extra rotation is very hard to do, but in a Bose condensate, if they start to rotate, you can see it quite easily. Now it turns out that for many years, beginning over 10 years ago, people have suggested doing exactly the experiment that we have done. The earliest one was Ewan Wright at University of Arizona in 1997, and the most recent one was John Dowling, now at Louisiana State, in 2005. And what they suggested doing was using a kind of a combination Raman-Bragg process, where they would start with a Bose condensate in a particular ground state, absorb light from a Gaussian beam, detuned from atomic resonance by some large amount, and then stimulate emission back down to a different ground state, say a different hyperfine state in the atom, and that beam would be a Laguerre Gauss beam, and therefore would impart angular momentum to the atomic cloud, which I've tried to indicate by having this be in the shape of a donut. So all of the theoretical proposals used this kind of a scheme. Now, in fact, that's not what we did when we did the experiment, but we have done that, and other people have done that. Nick Bigelow has done that since. But in fact, the first experiments we did, now can everybody see that green? You know, it looks like it's a little bit faint. But that's the trouble with using green. See, there's actually some green here, but it's supposed to be faint because we get rid of the atoms. Okay, so here's what we do. We start with Bose condensate, and instead of transferring from between two internal states, we transfer between two different linear momentum states plus two different angular momentum states. So this is why I've called it rotational Bragg, because it's just like the Bragg scattering I described already, but one of the beams is Gaussian and one of the beams is Laguerre Gaussian. So what's going to happen is the atom is going to absorb a photon from the Gaussian beam and get a kick in that direction to the right. Then it's going to be stimulated to emit a photon into a Laguerre Gauss beam. and that will give the atoms another kick in the same direction, and then we'll have a group of atoms going out this way that has orbital angular momentum. That is, the whole cloud is spinning. Now I want to emphasize how I think about this, which I think is a correct way of thinking about it. In the Bose condensate, every atom has a wave function that occupies the entire size of the cloud. We cannot think about atoms being one place or atoms being someplace else. Every atom is everywhere in the cloud. And when that atom absorbs a photon from the Gaussian beam, it absorbs it in its entire wave function. And when that atom is stimulated to emit a photon, it emits a photon in this strange Laguerre-Gauss mode, and it emits it from its entire mode, and conservation of angular momentum says that that means that its entire mode has to start rotating, and that's what we're going to see when we look at the cloud of atoms. So the process is, we start with the Bose condensate here, we do this Bragg scattering, a portion of the atoms are diffracted into this cloud that is moving away at 6 centimeters per second, because this is sodium, and that's 2 recoil velocities. Then we optically pump just the cloud that is moving away. Once it's gotten far enough away, we optically pump it into a state that will allow us to do a cycling transition. And then we image it from this direction. This cloud is invisible because it's not in the right state. We image this cloud, and then what we hope to see is a donut shape when looked at from this direction. Now what I'm going to do is I'm going to run a movie that sort of shows that process. We'll hope that it runs. Okay, so there's the Bose condensate. Then we do the Bragg diffraction. Then we do the pumping, and then we do the imaging. Okay? Chris Helmerson made that movie. He's really good at doing this. Okay, so here's the picture again. Bragg diffraction, which wasn't shown in the movie. Separation of the clouds, pumping, and then imaging. Okay, and here's the image. Just what we wanted to see, a donut. See, it's got a hole in the middle. And what I'm claiming is every atom is in a state having a wave function that looks like this. Now, the problem with this picture is, all it shows is that I've got a hole. Okay? Now, the laser beam that did the diffraction had a hole in it. So, of course, the wave function that is diffracted is going to have a hole in it. How do I know that this thing is rotating? Well, fortunately, a number of people who have been studying vortices in Bose condensates for some time have developed methods for determining whether this thing is rotating, for seeing the rotation. So in the first vortex experiments at JILA, they essentially made an interference between a rotating cloud and a non-rotating cloud. Now you see what happens if you add, now the thing you can't see so easily on here is the Gaussian distribution of intensities, because I didn't very carefully make a Gaussian distribution of intensities, I just made something flat. But if this thing has a hole in the center, and there's a phase winding around here, and this one is a constant, then what is going to happen is that this has a constant phase, this has a winding phase. At some point, the phase of this thing is going to cancel. It'll be the opposite, 180 degrees out of phase for this one, and at the place where the two have the same amplitude, you'll get a hole. So what happens is when you add this one to this one, the hole moves off to the side, because it has to be at the place in the cloud where the two clouds have the same amplitude, and that's going to be somewhere off to the side, because this one has 0 amplitude in the center, so it's not going to cancel in the center. It's only when you move out to the side where you have the thing having the same amplitude as the uniform phase cloud, and so seeing a hole off to the side is an indication that it's rotating. Now, at the École Normale, they did a slightly different one. They did an interference between this rotating cloud and a uniform cloud, non-rotating cloud, that's moving a little bit. So not only do you move, so you're not interfering with a constant phase, you're interfering with a phase that has a linear gradient, because that's what motion is. Motion in quantum mechanics is just gradient of phase. So now you've got something that has a gradient of phase, and you'll see that when you add something that has a linear gradient to something that has something that's rotating, you get this fork structure. Now look, that structure is identical to the diffraction grating that you use to make the Laguerre-Gauss beam in the first place. Why is that? Well, I think that maybe another one of my slides will make that a little bit more clear. I hope it will. Yeah, okay, it will. So we'll just come to that a little bit later. So here's the let's see. Okay, right. Am I going the wrong way? Yeah, I'm going the wrong way. Okay. Okay, so those are the methods. Here's the results. Here's what we did to do this process. Here's the first process you've already seen. This creates a spinning condensate moving off. Now, the spinning condensate that's moving off is shown here in green, but they're right on top of each other. And before they have had a chance to separate, I hit it again, but now with two Gaussian beams. The two Gaussian beams is just ordinary Bragg scatter. So now I've got two Bose condensates heading off to the right, one that's rotating and one that's not. That's just what I want, right? I get rid of the one that's not moving by the optical pumping process, and then I image the two clouds that are moving and look to see what I've got. And sure enough, here's what I get. The whole has moved off to the side. And here is a simulation of what you would get. And here it sort of shows the idea. Here, phi is constant, and let's say that phi was, in this case, was minus pi over 2. Then here, phi winds up by 2 pi. Here, where it's plus pi over 2, the two interfere destructively, and they make a hole. Okay, and here's the data. Now the other one, where we interfere with a slightly moving condensate, almost the same thing. Here's the thing that produces the original spinning condensate. Here's two Gaussian beams, so it's not going to be spinning, but one of the Gaussian beams is tilted a little bit so that the momentum transferred is not exactly the same. So now I've got two clouds going out, but the two clouds don't have exactly the same momentum. So they're going to have a standing wave, but because one of them is rotating, the standing wave gives this fork. So here's the idea. Here's the one that's moving. You see it changes in phase from pi to 0 to minus pi to 0 along here in this linear direction. This one is rotating. So up here at this, at the top, it's got a phase of pi over 2, and down here at the bottom, it's got a phase of 3 pi over 2. So if I count how many fringes I'm going to go through, depending upon whether I pass along this side or along this side. You see here there's an extra pi that I pick up if I go along this edge compared to going along this edge, and so I get an extra fringe, or maybe one fringe less going along this direction than I do going along this direction, and that's how the fork shows up. And here's the data. It's not wonderful, but you can see that it definitely has that forked structure. So that forked structure comes because if I go on one side of the cloud, the total amount of phase that I pick up is one thing, and if I go on the other side, the phase that I pick up is something else because of this rotation. And then when I interfere it with the constant phase, or with, well, this constant gradient of phase, then I'm going to have this difference. Well, let me say that again. If I go from here, along this side, I'm going through a phase that goes from pi over 2 to pi to 3 pi over 2. When I go along this one, I go from pi over 2 to 0 to minus pi over 2, which is the same as 3 pi over 2. So here, the phase is going down as I go down, and here the phase is going up, right? Because the rotation, you see, means that the velocity in this case is going up, and the velocity here is going down. So the way in which the phase changes as I go down this side is different from the way in which the phase changes as I go down this side. It's the opposite direction. So when I add that to something that has a constant gradient of phase, I'm going to pick up one less fringe on one side or on the other, and that's the thing that makes the fork. Now, if I've got, let's imagine these were two light beams instead of two atom beams. It works exactly the same way. Okay, if this was a Laguerre-Gauss beam and this was a Gaussian beam, I would interfere the two beams, and this would be the interferogram. Think of that as being a hologram. Now what happens when you make a hologram? You read out a hologram by shining in the reference beam, and what comes out is the object beam. So if this was the object beam and this is the reference beam, if I shine a Gaussian beam onto this hologram, what's going to come out is the Laguerre-Gauss beam, and that's the explanation for why a forked diffraction pattern produces a Laguerre-Gauss beam, because it's just the hologram formed from the interference of a Laguerre-Gauss with a Gaussian. You read it out by putting a Gaussian in, it comes out as a Laguerre-Gauss. So that's one way of thinking about why it does that. Okay, so that proves that our cloud is rotating because we see the forked structure when we interfere it with a non-rotating cloud, or we see the offset of the hole. Now, there's some more complicated things which I think I'm going to skip because let me go to this thing. Have we done the process coherently? Okay? That's a legitimate question to ask. We think we have, because the laser beams are coherent, the Bose condensate is coherent. We should have a coherent addition of angular momentum. Well, one of the ways in which we can find out whether it's coherent is to see whether the phase of the rotation of the cloud is tied to the phase of the lasers. So because our lasers are not perfectly phase stable, what we do instead is we measure the phase of the lasers using a simple interferometer. And here's the interferogram, and that tells us what the phase of the lasers is. And we compare that phase to the phase that we see in the atom interferogram, which is given by the angle between the hole and the center of the cloud. So here the angle is like that. So we do this for a bunch of different angles between the two laser beams and plot the angle of the atoms compared to the angle of the light, and we see that we get a straight line that shows that the angle of the light, that is the phase of the light, and the phase of the circulating atoms are completely correlated. So we know that it's a coherent process as well. We can do higher order, but I'm not going to bother with that.
How do you set the zero phase there?
Well,
because it's modulo 2 pi anyway.
Yeah. So it's right. So as far as zero, it's just arbitrary. All we're saying is that there's a linear relationship between the phase of the atoms and the phase of the light. So yeah, that's really all we're saying.
But
and
then
then
the difference of the phase of the two Gauss and Laguerre-Gauss.
Right, exactly. And setting that zero, again, it's arbitrary. I could say that I want it to be the same phase at, straight up at 12 o'clock. It's an arbitrary choice where I say the two things have the same phase. Because one of them has a constant.
But with here is the phase difference between the Laguerre-Gauss and the Gaussian.
That's right. That's what I measure with.
That matters.
That's right. That's what I measure with this interferometer. Here, I'm measuring the relative phase between the two optical beams by just interfering.
Because here you did not show it as a Laguerre-Gauss.
Here's the holographic radial. So that's the Laguerre-Gauss. Yeah. I'm sorry. I should have perhaps made that with a hole in the middle to make it clear. Okay. Okay, so now, for the final part, which I've probably already gone on too long, I want to show what happens when we use these same kinds of techniques to spin atoms in a toroidal trap. And a lot of people have talked about things that you could do with toroidal traps. I won't go through all those details. I'll just say that we decided it was a good idea. Other people have decided it was a good idea. How do you make a toroidal trap? Well, probably the first toroidal trap for a Bose condensate was made by Wolfgang Ketterle when he made his first Bose condensate of sodium atoms, where he had a magnetic trap. It was a quadrupole magnetic trap, and he put a blue detuned laser down the center of that trap and made kind of Mexican hat potential. So that's what we're looking for. We're looking for a Mexican hat potential, and that is one way of making it. Another way of making it would be just use a Laguerre-Gauss beam. We've been talking about Laguerre-Gauss beams. They will make a toroidal-shaped potential. If they're red detuned, the highest intensity is on a ring, and you can make a Mexican hat potential. You're okay with Mexican hat as a characterization of a? Okay. So you can make other versions of a magnetic field. Here's a purely magnetic trap that could make a toroidal trap, and this is being done by at Berkeley. Dan Steinberg-Heron. Here's the old MIT thing. Chandra Raman at Georgia Tech is also doing this. And here's our version. We took a top trap. We put a blue detuned laser down the center of the top trap, and here's the potential that we got. But for whatever reasons, I think it mainly has to do with the fact that we had lots of atoms, so we had a big chemical potential. We had a small trap, so there wasn't much variation of the potential around the trap. We were the first ones who were able to make a continuous, coherent condensate that filled the torus. So here's some details about the various sizes and everything of this trap. Let me show you a movie of starting with an atomic cloud in a magnetic trap, and then you turn on a blue detuned laser beam to force the atoms out, and we were able to do that in such a way that the condensate remained coherent. So here's how we spin up angular momentum in such a trap. We can make such a trap, it's toroidal, but there's no rotation. In order to rotate it, we do the trick with the rotational brag, but we have to have another trick, because remember, up until now, all the pictures that I've shown you of rotating clouds were also moving with 6 centimeters per second, because we had done both brag for linear momentum and for rotational momentum. But we don't want that now, because now we want to hold the atoms trapped. Those atoms were all free moving. So first, we give it a linear momentum kick without any angular momentum, while the atoms are in the trap. And before they have had a chance to move very far at all, we give them another kick back with a Laguerre-Gauss beam. So all the atoms that are transferred back are rotating. The ones that are not transferred back, like the ones that are in the hole, are still moving. We get rid of the ones that are moving, and what we're left with are atoms that are in the trap, because they've been given a kick, but immediately given a kick back, so they're not moving. They have very little linear momentum, and but they should be rotating. So here is a picture of the atoms after time of flight. So let me go back to this is a picture in situ. It's got a hole in the center, okay, but it's not rotating. The reason it has a hole in the center is because the atoms aren't allowed to be in the center, okay? So we can't tell by looking in situ that it's rotating just because it has a hole. Here is the cloud after time of flight. It has a hole. Here is a Bose condensate where we did not transfer any rotation after time of flight. The hole fills in. Okay? So this, as it turns out, although it may not be convincing the first time you do it, and you want to do something else to be sure, but if you let the cloud expand, if the hole remains, then the cloud is rotating. If the hole goes away, then the cloud is not rotating. Or if the hole is too small to see, as is often the case with vortices, when you expand it, you get a hole, and that tells you that there was a vortex, that the cloud really was rotating. If it's not rotating, the holes will fill in. So we know that the atoms are rotating because of the fact that the hole persists in time of flight, but we can do other experiments. We can do velocity selective. Yes?
Quickly there. So then I'm a bit confused about the scaling parameter. And on the one hand, it seems that on the one hand we say, okay, when we have vortex, we make time of flight.
Yeah.
we see the vortex expand,
Right.
and everything is self-similar in scale.
Well, not
And
quite
yet-
self-similar. It's not really self-similar, I don't think. Is it in the case of?
No, that's right.
is filled
Is filled,
in
right?
the time of
In the time, well, right. So okay, so I think I can explain it in hand waving, but maybe you can give a better explanation afterwards. If I've got a non-rotating BEC, then so here's a kind of an annulus, okay? Well, let's just say that let me go to one where it's actually, okay. So let's say here it is. I have this annulus. Look across here. The velocity of those atoms is going to be both radial and that is out and in.
Yeah.
And so when you release it, atoms are going to go in and they're going to go out. But when the atoms are rotating around like that, then they can't end up going into the center because you have to conserve angular momentum in the whole cloud. And so there's no way you can fill in the hole and still conserve angular momentum. Okay, now, do you want to give a more sophisticated?
It's a question of phase again.
Yeah.
Like this.
Okay.
I agree.
But if you are in the ground state of a toroidal track,
Well, the ground state would be not rotating, right?
I'm in the ground state, but
Yeah.
I still need to go around 2 pi and come back to the same point.
Well, but if I'm in the ground state, then I don't have any phase winding around the toroid.
Well, the Earth rotates and so forth. So
But the ground
you
state
will have to
of
be
the
careful
toroidal
about
track.
which reference frame you.
Yeah, but if I'm in the frame in which I created it from a static Bose condensate, then there should be no phase winding around. Now, it's true that Brian Anderson has done these these experiments that show that sometimes you can condense into a rotating state. I think that has a lot to do with time scales. I think of course, if you put in a plug like this, it's far more likely that if you, because of phase fluctuations, condense into a rotating state, that it'll stay that way. So that's another issue that I think is very interesting. But if we take the usual Bose condensate, and if you start the way I sort of showed this one, where you condense first into the magnetic trap and then pierce it, it's very unlikely that there's going to be a vortex left over from the evaporative cooling if you wait and equilibrate for a long time. And so this thing won't have any rotation around here. Well, actually the picture shows rotation, but that's because it's just trying to indicate that we put rotation in deliberately.
Let me just,
Sure.
suppose I have the ground state of a toroidal track. The wave function has to
I mean,
have...
not rotating.
Not rotating.
Okay,
But I'm just understand the phase.
sure.
The wave function has to have a phi dependence. I'm calling phi the angle.
No, but then you can have zero phi dependence, right? So for example, let's, if I,
How come
The ground state wave function is real. You can choose the
so for example, this could just as easily be the wave function of the atoms. This would be the one that's rotating, but I could suppress this part, okay, and suppress this part, and now this is just a Gaussian. That's a perfectly good wave function. Okay, the dependence here is it doesn't have to have any phi dependence, right? So that's a perfectly good wave function, just a plain old Gaussian wave packet.
As a function of phi.
Yeah, I mean, it doesn't have to be a function of phi. And as you say, the wave function, I can choose the wave function to be real. In that case, I can't choose the wave function to be real if it's rotating. But if it's not rotating, I can in fact choose it to be real. Yeah.
I have a question that I don't know if it completes this discussion, but is it possible to have a cloud with no holes that is rotating?
No.
No.
Okay, so let me say something about that. The reason is, in order to have rotation, you have to have a winding of phase. The phase, of course, has to be continuous, so it has to wind by multiples of 2 pi. Someplace, that is the place, that means if I go around some point, some center of rotation, it has to wind up by 2 pi. At the center, the wave function would be ill-defined if there were any amplitude there. So I must not have any amplitude exactly at the center. And I think it's a very general thing. I can't have hurricanes without having an eye of the storm, you know? But I think for a quantum mechanical wave function, it's easy to understand why you have to have an eye. I'm not sure I know the answer for for classical fluids, but it seems to be pretty general that vortex motion requires a singularity at the center of rotation. Does anybody know anything about classical fluid?
So I think that in a classical fluid you have a dip, but not necessarily the density that goes to 0 at the center.
Sure.
No, but if you quantize the angular momentum for each particle, you need to have 0. That's not required. You can have a distribution of angular momentum.
But you have also nuclei that rotates, they have angular momentum, they present spectrum of angular momentum, but density that they are not considered with any eye. That's
Yeah,
only
I guess that's right.
rotation.
But on the other hand, I mean, nuclei, who understands nuclei? but if you, I mean, take an atomic wave function, electronic wave function, the p states all are 0 at the center, right? Because they've got angular momentum. So it's for the same reason. You can't have any value at the center if you've got winding around the outside. I don't know about nuclei. Probably it has to do with the intrinsic.
They are described by Wigner D functions, for instance.
Yeah.
Then you have some it's a collective motion. In nuclei, you have some collective motion of the constituents.
And of course, you've got really strong forces between the nuclei, so it's a very highly correlated
I think
system.
that it depends on the density of which kind of fluid that you have.
So this is obviously an extremely interesting subject because everybody's talking among themselves about it. So I suggest we come back to the speaker now, and then we'll continue the discussions about singularities and wave functions a little bit later. Okay, everybody pay attention up here now. Okay, so just to be sure, we made some direct measurements on the velocity profile of the atoms in the rotating frame by doing velocity-selected Bragg scattering. Now, up until now, I've just described Bragg scattering as transferring momentum from every atom in the condensate so that they were all moving. And that will happen whenever the Bragg pulse is short enough that it has a Fourier spread that is big enough to encompass all the different kinetic energies that the atoms will have when they are in the final Bragg state. But if the Bragg pulse is long enough, then it will not have enough Fourier spread to excite all of the atoms, that is to transfer all of the atoms. It will only be able to transfer the ones that match the energy conservation condition, and that will depend on the velocity, and it will depend on which direction the atoms are going. So by changing the frequency between the Bragg beams, we can diffract the atoms that are on the bottom that are moving to the left, or we can diffract the atoms on the top that are moving to the right, and we can see that as a function of the frequency that we can diffract more on the top or more on the bottom, and we can see, well, we can see directly from the pictures that the cloud is rotating. So there's no question, by doing Doppler measurements of the velocity, we can show that the cloud is rotating. So now, for the denouement of this whole idea, what good does having a toroidal trap do? And here is what good it does. When we excite a rotation in our cloud, but do not have the plug in the middle to make it into a torus, so it's just an ordinary Bose condensate, we excite rotation just as in the same way I described before. So we now have a vortex in the cloud. Here is the lifetime of that vortex, half a second. Well, half a second's a long time, but it goes away after half a second. When we do it in the toroid, it doesn't decay until about 10 seconds, and then it decays with a lifetime of a few seconds. There's no decay at all for 10 seconds. In other words, it lives a really long time. And we know why it finally goes away. The reason it finally goes away is that the platform on which the laser beam rests and the platform on which the magnetic trap rests are two different platforms. And one of them is constantly being heated and cooled as we evaporate and re-trap atoms, and the other one is just sitting there. And so the magnetic trap moves a few micrometers compared to the laser and pinches off the vortex. And this is the best we could do, trying to follow the magnetic trap by moving the laser beam a little bit. Actually, I think we moved a compensating magnetic field in this case. But we could keep it for a little longer than 10 seconds by those compensation techniques. So it's a technical thing that makes the thing finally go away. And what we have instead is that when there is no
wasn't by this technical problem, this would be
it would be
persistent.
persistent, right? So that's what we're claiming, is we've got a persistent current when it's in a toroid, and it's not a persistent current when it's in a bulk Bose condensate. So now we might ask the question, how should we understand why it is stable? And what I want to do is to offer you two different explanations and not tell you which one I think is the right one, but leave that for you to tell me. So one answer is what I call the global answer. If I have circulation around here like this, then that means the center of rotation is somewhere here in the center of the toroid where there are no atoms. Now we know from the discussion we just had that we must have a hole at the center. And here, there's no problem. There is always a hole there because the atoms are excluded from there. Now, in order to have this rotation go away, I'm going to have to, remember, this is a quantum mechanical wave function. It has to wind up. So I can't just slow it down and have it go a little bit more slowly. That's not going to work. It has to, it's quantized. So the way in which I get rid of this vortex is I move it into the region where there's atoms and then out. In fact, that's the way a vortex is lost from a bulk condensate. The center of the vortex drifts to the edge of the condensate, and then it's gone. And I want to learn more from you about the life and death of a vortex, because you were telling a little bit about that in the lab the other day. Yeah, so we'll discuss that a little bit later, because I want to see whether there's anything more I should know about this. But that's the usual way. The vortex moves to the outside, and then it goes off into the places where there's no atoms, and there's no problem. But you see, in order for this thing to be lost, it has to go from a place where there's no density to a place where there's a high density. Making the density of the condensate go to zero costs energy, because it has to go to zero over a very short distance, the healing length. And it costs kinetic energy to make something change that rapidly. So there's an energy barrier. It costs energy to move this thing out. So there's an energy barrier to moving the vortex out of the torus, and so it'll be stable energetically. So that's what I call the global answer. There's a local answer. Imagine that I'm sitting here in this torus, looking at the atoms flow by. The atoms are superfluid. The superfluid, we know from Landau's theory, that the superfluid flow will be dissipationless unless I exceed some critical velocity. So as long as I'm going slowly enough, then I should not dissipate this flow, because I can't, there's no way I can dissipate the flow and still conserve energy and momentum if I've got a phononic dispersion relationship for the excitations in the superfluid. So locally it should be stable, globally it should be stable, but these two explanations for the stability sound like they are completely different. Now here's my problem. I go to my friends who are condensed matter physicists and work in superfluidity, and I say, well, what about this? And some of them say, well, this is the right answer. The global answer is the right answer. Just forget about that Landau stuff. He didn't know what he was talking about anyway. And then I go to other people, and they say, well, that's exactly the same thing. Those are two ways of looking at exactly the same thing. I say, oh. because I'm not sure I see that they scale quite in the same way. I mean, if I ask, well, anyway, let me not go into the details. Let me just encourage you to be thinking about this problem, because I think it's an interesting problem. Why is this stable? And more particularly, how should I understand the relationship between these two different explanations? Let me just show you a few other things. This vortex motion, this rotational motion, is very robust against all kinds of things. This shows the probability of still finding the vortex in there after we release as a function of the temperature, which is here the BEC fraction. So it turns out until you get the BEC fraction quite small, which means very close to the critical temperature, it is stable. Obviously, if we took away the plug, it would not be stable. So how far down can we turn the plug? Well, it turns out when we reduce the height of the plug to about the chemical potential, perhaps that's no surprise that that would be the scale, then it becomes unstable. But as long as the plug has a potential barrier that is larger than the chemical potential, then it appears that the thing is stable. By using...
It's not 1 unit of mu here.
It's 2, yeah. So why it's 2, I don't know.
Tunnel effects, perhaps.
Good. Yeah, that may very well be. I think it's an excellent question. It's one of the things I would like to learn, is why it's 2. I mean, it's going to have to be the order of the chemical potential. But why 2? I don't know. I mean, when we first did it, it looked like 1, and we were really happy, and then we did it more carefully, and we found that it was 2. And we thought, oh, gee, why is it 2? I don't know. But maybe I'm sure we can learn that.
So 2 is better than 0.5, because 0.5 is basically.
Sure. So I don't know. I don't know why 2. Okay, so here's something else we can do. We can transfer as many units of angular momentum as we want to this cloud, either by doing the rotational Bragg scattering more than once, by doing it with 2 Laguerre-Gauss beams that are going in opposite directions, by using a higher order Laguerre-Gauss mode, any number of ways. So here is a case where we did that. We transferred 2 units of angular momentum, and then we held it in the toroidal trap for a certain length of time, and then we released the plug, took the plug out, and let the atoms stay in the 3-dimensional trap for a little bit of time. Now, when we look immediately after removing the plug, we see a single great big vortex, which means there's 2 units of angular momentum going around here. But as we wait longer, it breaks up. Now, this has been known for a long time, that if you have a multiply charged vortex, it's going to break up because it's energetically favorable to be 2 rather than 1. You can just figure out what the energy is in a highly charged vortex, and you're going to have a larger energy. The point is that when it's in the torus, it's perfectly stable. There's no way that that thing can decay. Only when we pull the plug will the winding number of 2 decay into 2 vortices. So this should provide an interesting way of studying the decay of multiply charged vortices, because we can produce anything we want. We have a starting point for the decay, and we should be able to study the thing as a function of the charge of the vortex. Other experiments that have been done have had limitations on what charge can be produced.
I think both of them measure many different charges.
Not many different charges, because he could only, the technique that he used for making multiply charged vortex was one where the magnetic field was reversed in a sample, and basically you were just stuck with whatever that process gives you, which I think was 2 or 4 depending upon what you did, yeah.
You said before that putting a hole somewhere else in the donut, it's very costly, energetically very costly. But also, I mean, do you think if I charge the vortex enough, I can have, I mean, I will have a competition, right, of 2 phenomena, because I will have a very charged vortex that will want to break down in another vortices.
Yeah.
But of course, I have this energy barrier for having vortices somewhere else.
Yeah, so that's an interesting question. the highly charged vortex always has lower energy if it breaks up into multiple singly charged vortices. But you've raised an important question. Is there a barrier to go to that lower energy state from the multiply charged vortex? And I don't know the answer to that. I think that's maybe there are treatments that show that energy barrier, but I know that there are some theoretical treatments of the breakup, but I don't know if they're analyzed in terms of an energy barrier. I think that would be a very interesting analysis, because then you'd ask yourself, well, what's the tunneling rate from this multiply charged system in some sort of energy space into the singly charged? So we know that it's energetically favorable to break up, but what prevents it from breaking up, or what delays it breaking up, isn't so obvious. It's clear that a doubly charged vortex doesn't break up as quickly as a quadruply charged vortex. And it's also interesting what kind of configuration it breaks up into. That is, let's say I have 4 vortices. Are they going to break up immediately into 4 ones, or are they going to break up into 2 twos, and then the 2 twos are going to break up into ones? Well, we can't tell that yet, but we can see that some of our multiply charged vortices, when they break up into interesting patterns, regular patterns of vortices. So there's a lot of questions like that that are not yet addressed.
I have another question about the previous slide. And so did you try so when you start the stability starting with the normal condensate or the one with the plug, you try also to see what happens if you start with the one with the plug and then you remove the plug.
Yeah. Okay.
So as soon as you remove the plug, it decays away, or?
Okay, so that's a good question, and I don't believe that we have very much data along those lines, but I think that generally, if I remove the plug, it decays away quickly. I mean, so just to summarize, the question is, if we make a vortex in a condensate without a plug at all, is there a different lifetime than if we make it in a torus and then remove the plug and ask how long it goes away? And all I can tell you is that my memory is that in both cases it's short, but whether it's the same, I can't say. I think that would be an interesting thing to learn as well.
This would help to understand between the two possible explanations if they are equivalent.
Well, maybe so, but one of the difficulties with answering these questions is that there's other stuff that comes in. The vortices that we make are not the lowest energy singly charged vortices, because we make them in such a way as to not be the lowest radial excitation of the vortex. We make them to have the lowest non-zero winding number, but they don't have the right radial shape because the electromagnetic field of the light doesn't match the core size of the vortex, so they're going to be excited along that direction. When we pull the plug out, we can pull the plug out adiabatically or non-adiabatically. If we pull it out adiabatically, then probably we're going to go to the lowest radially excited vortex state. And if we pull it out non-adiabatically, we'll probably make something even more excited than we do when we do the angular momentum. And so those excitations might affect how fast the thing decays. So yeah, so I'm not sure we would end up with simple answers even if we did those experiments carefully, which we haven't done. Yeah.
When you make the spinning cloud in the boson synchronous of the free, when you turn off the trap and it's falling down and you're spinning it, the rotation does not disappear, right? It should be stable, is it?
Yeah.
I'm trying to understand if the decay of the spinning rate has something to do with the presence of the trap.
Okay, so let me emphasize, there isn't any decay of the spinning rate. Either there's a vortex or there isn't.
Right, decay.
So that's all we measure, is whether there's a vortex or not.
Right.
So what we're looking at is probability that there's one there. So,
But the presence of the trap, does that influence this probability?
yeah,
Survival probability?
yeah, right. I mean,
And if you don't have the trap, it should stay on forever, even if it's not enough harvest.
yeah, so that's true. If I turn the trap off, then of course the cloud expands.
Right, but in the...
But it will always have the rotation. And I think that one way of understanding that is the following. Everything about the dynamics of what happens to a vortex is dominated by the interactions between the particles. If there aren't interactions, then the vortex can't escape. I have to lose energy in order for the vortex to escape. So the only way I can do that is by scattering phonons, for example, off of the vortex as it moves out, or other processes. If we let the cloud expand, at some point it collisionally decouples, and no more of that sort of thing is going to go on, and I'm just going to have the single particle wave function behavior, and it's just going to go on forever. So I think that's right. If I let it expand enough, then nothing more is going to happen. All of the properties are going to be frozen into the condensate once it becomes non-collisional.
I'm just a little confused. When you have the cloud on the lexical rotation, you think that that's a vortex or it's just a spinning cloud?
Well,
which happens
yes.
to be in that potential.
Okay, so
and then decay to a vortex
Yeah,
later on.
that's
because you have that stability, and we are saying, well, vortex is very stable.
Yeah.
What is stable there is just a rotating.
Yeah, so I've been a little bit careless with my language. I probably should not call the rotational state in a toroidal trap a vortex, because we should probably reserve the word vortex for something in a bulk fluid where the core size is something that's related to the healing length. Here we have artificially made a great big core, and it's not because of the interactions, it's because of the shape of the trap. So when I say vortex in the toroidal trap, I probably should not use those words. I should probably just say a persistent current state or something like that.
I would disagree,
Okay.
because the first Gila experiment with the two states, BEC was clearly a vortex with a winding number of 2 pi, and the core was artificially much larger because this was the second species BEC. So
Okay, well, you're right. That was, but I do remember that a number of people criticized them and said, this isn't a real vortex, it's a skyrmion or something like that. But I don't know,
But there was a winding number.
There was a winding number.
Clearly established. So
Yes. So it depends on what you're trying to demonstrate. Are you trying to demonstrate that you've got irrotational flow, that the wave function has to be continuous? Either one of these things will do that. If you're trying to demonstrate that it ends up with a core size that is the one predicted by,
that's different.
that's different. And then you need to have this. So, I mean, maybe we shouldn't worry too much about terminology, as long as we're clear about what we're looking at.
Well, I thought the vortex is a spontaneous solution when you have a rotation in some conditions.
Well, that's
I
certainly...
can rotate and I don't have a vortex.
Well, I don't think that if you've got a condensate, if you've got a coherent wave function, the only way you can rotate is to have a vortex.
That's Feynman.
Yeah, but I can start to rotate the cloud and I don't have a vortex yet.
Well, I don't think you can. Let's think about this a moment. First of all, rotating. Okay, you've got a comment that'll...
Yes, well, not on this
illuminate
issue,
this.
actually on something you said a little earlier. Could you go back, please, to the slide where you show the local versus the global argument for stability? I have a remark on the Landau criterion and a question related to that remark. The remark is that the original form of the Landau criterion works by looking at the slope of the dispersion relation of the tracer particle excitations. When you apply that to a BCS superconductor, where we know how to calculate the critical velocity, the critical current, you find that the Landau criterion gets at best the order of magnitude right.
Yeah.
It's not quantitatively reliable. So Landau, he knew very well what he was talking about, but his criterion is an order of magnitude estimate. It's not quantitatively reliable.
Fair enough. Now
And related to that, a question. Can you supply in your experiments enough orbital angular momentum to drive the system normal optically without heating? That is, can you exceed the critical velocity?
I believe we can, but we haven't yet done those experiments. Or, well, I'll return to that perhaps a little bit later. When we tried to put 2 units in, we found that it wasn't very stable until we made the trap a little bit bigger. Now, why was that? That would be an interesting thing to fold into this question. Okay, now let's return to Vanderlei's question, because I think it's a very important one. Let's imagine that I've got a trapped cloud. Now, I want to rotate it. How do I do it? I think the only way that I can do it is to make the trap a little bit asymmetric. Then I can rotate that trap. Now, I think, if my understanding is correct, until I bring a vortex in, when I rotate that trap, I don't impart any rotation to the cloud. If I'm in the lab frame and the potential is rotating in the lab frame, then I am not going to impart any rotation.
Any flowing.
Right. If I was to look at the rotation of that cloud before I bring a vortex in, there won't be any rotation of that cloud. Now, if I go, there's a critical
threshold for the rotation,
and the vortex comes in from the outside.
above which it can enter.
Now, if I go into the rotating frame, then I find that, of course, in the rotating frame, things are different because I've got extra terms in the Hamiltonian. So in the rotating frame, I find that at a critical point, the lowest energy solution is a vortex. So to get rotation into the thing, I always have to have.
Yeah, but here it's a little different, right? Because having your when you bring the angular momentum to the, so it's like I can give any velocity and still be okay.
I don't know. I can't. I cannot have any velocity other than ones that satisfy the quantized rotation condition. So I have my toroidal trap. Not all velocities are allowed. Only the quantized ones are allowed. In fact, in this sense, it's very much like the superconductor case. If I've got a ring of superconductor, I cannot have arbitrary current. Only the ones that correspond to having one flux quantum thread the superconductor.
I thought the way you started, like making the trap and everything, but the problem is you are not giving any velocity before you condensate. I can't think that I condensate the whole thing.
Okay, now that's a very good point. Let's imagine that I did give it some velocity before I condensed. So here is, I believe this is called the Fairbank-Hess experiment. Imagine that I have an angular sample of liquid helium, but above the lambda point. And I rotate it. And it's a classical liquid, okay? And I rotate it at a velocity less than half, if I'm remembering correctly, half the velocity required to have 1 unit of winding number. The classical fluid will rotate with the container. Now, while rotating, I cool it down to the lambda point. The fluid will be static because it cannot support that rotation. If I made the rotation higher, it would, when it cooled down, it would be rotating with 1 unit. Okay? So that is one of the features of what is sometimes called superfluidity, which has nothing to do with whether there are interactions or not. It has only to do with whether or not you have an order parameter, something that represents a macroscopic quantum phase. Now, Tony Leggett is very insistent that we misuse the term, regularly, that we misuse the term superfluidity, which is not a single phenomenon. He says, in fact, the term we use for superfluidity is a number of different phenomena, one of which is that one, which has nothing to do with interactions, another of which is, a different phenomenon is one in which we have dissipationless flow through an orifice or something, and that does have to do with interactions, and that's a different phenomenon, but they happen to occur at the same time. But he claims they are different physical phenomena. They don't have to do with the same thing. Well, I think with atomic gases, we have the opportunity for studying these different things and for turning the interactions on and off to find out how these kinds of things behave. So we can do things that can't be done in liquid helium. So, but you know, this Fairbank-Hess thing, I think, is one of the key features of superfluidity, and it addresses the kind of, and it's very counterintuitive. I mean,
and also you are so worried about the size of the core.
Yeah.
But that's what we have when we have a, you know, like the Pitayevsk type of,
right,
which is uniformly fluid with some density.
Right. So if you have a uniform fluid,
and then you put local heat length,
and then you put an
solution
excitation in it.
Long ago, but here a vortex may be something that's conjugated to the potential change. So,
well, yeah. So but
I'm going back. Maybe we can call vortices.
But I think that there it's just a matter of terminology. Maybe we shouldn't call it a vortex. Maybe we should. I don't know. I don't really care as long as we're clear about what it is. But the thing we make is not. It's a vortex that is when we don't have the plug in there. It's certainly a vortex of some sort. It's just not the lowest energy one. I'm sure it quickly decays to the lowest energy one. I'm sure that vortex, that its core size is too big, sheds some phonons and goes down to the one that you get for the lowest energy solution. But we haven't looked at that, so we don't know for sure.
May I add a comment about this issue of Landau criterion? The Landau criterion has to do with the energetic, so if it is not favorable from an energetic point of view to create excitation.
Right.
But the creation of vortices, for example, is a dynamical process.
Yes.
So you can be above the critical velocity, you are in a metastable state, and you create vortices by dynamical instability. And
Okay.
this explains why the critical velocity for creating vortices is well above the Landau critical velocity.
Well, I'm not sure it always is. For example, let's say that my understanding is the following. If I had an atomic gas superfluid, a Bose gas that was superfluid, and I were to drag through it an object that was larger than the healing length, then I would have dissipation through the creation of vortices at a velocity lower than the sound speed, which would be the usual Landau criterion. On the other hand, if I was to drag an object that was much smaller than the healing length, I would generate phonons only when I exceed the sound velocity. But your point about...
so my point was about the Paris experiment, when you rotate the deformation of the shape.
Yeah.
So in that case, you have to consider the instability of this deformation.
Yes, that's right. So I absolutely agree there. I mean, that rotation, that has to do with the whole, you have to ask what is the energetic stability of that rotational motion and whether that will lead to a vortex. It's not, you don't have to rotate at a velocity that's related to the Landau critical velocity in order to generate vortices. You just have to, well, I'm not sure just how, what velocity would you talk about? Because obviously it's not rigid. It's not rigid rotation.
Now, in that case, you have to consider the deformation that you use for rotating the cloud, and then it was demonstrated by Van Casten that you study the dynamical instability of this deformation.
Yeah. Yeah, I think that's right. I think probably we should discuss that in more detail afterwards.
Anticipation with the superfluids, something interesting. That would be related to the...
I have a whole discussion about whether this is quantum, but I'm not going to go there. I'm just going to remind you of who all the people are and show you a picture of a few of them. Because I think that this has been a wonderful discussion, and I thank all of you for a lot of stimulating questions. But I
can't see the name of the first person.
Oh, I'm sorry. Yeah, you're right. It's really terrible. His name is Anand Ramanathan.
Oh, this is the student.
Yeah, this is the student. Okay. Yeah. He's a very good student too. So that's the end. Thank you very much.
Well, very nice.
I think
Pode dar um beijo na Bel.
Very interesting question. You can have orbital angular momentum, but there's no